Today we are considering the numerical methods for solving optimization, specific the nonlinear programming problem. In the last class I discussed about the classical optimization technique for solving nonlinear optimization problem, but there was one restriction for that function must be at least twice differentiable within the domain of definition, but where the function is discontinuous, is not defined within the whole feasible space. How to develop the optimization technique for that? The numerical technique, numerical method is most popular in that case, and numerical methods are applicable for constraint as well as unconstrained optimization problems, specifically nonlinear programming problems. And numerical method is mainly based on the searching procedure, and it searches for the local optimal in the feasible region. Now, let us consider one, and this is mostly iterative process. We start from a point on the feasible space and we move to the optimal point after certain iterations. Now, let us consider a hypothetical two variable nonlinear programming problem, and just I will discuss how the iterative process run on this problem to get the optimal solution for the given problem. For this, let us consider one problem that is of two variables x1 and x2. And this is, let us consider in general the constraint optimization problem. That is why we are considering there are three constraints: constraint 1, constraint 2 and constraint 3, and this is the defined feasible space for us. These are all nonlinear in nature, all the constraints, and this is forming the feasible space here. Now, if we have a function which has to be optimized, let us consider the minimization of the objective function, where objective function is a circular is a circle. That is why for different value of the function, it takes different place in the feasible space. If this is one of the place where functional value f is equal to say C1, where function is this is a part of the circle. There is another, since this is a minimization problem, we will try to minimize the objective function f here. That is why we will just find out the space where the objective function is minimum. Now, this is the next, this is another position where functional value is a C2. In that way, we can minimize function further and further. How long? That depends on when the functional value is out of the feasible space, that time we will just conclude our journey. That is why I can say this is the space where the functional value is the minimum, and this is the corresponding optimal point here. Now, let us consider this is the functional value is C1, this is C2, this is C3, this is C4, this is functional value is C5, and there is further, if function moves here, then functional value is C6a, and this is the center for this, and it is clear that if I just move to functional value at C6, that will be out of the feasible space. That is why we need to stop our iterative process. If we start from f is equal to C1, it will move to C2, it will move to C3. That means we are getting better and better functional value. Once we are reaching to this point, functional value is coming is equal to C5, and this is the corresponding optimal point. If this is the process for us, how really we have started our started to search the feasible space? Just see, this is a searching technique I am now discussing with you. Now, this is first starting point for me. This is the point which is within the feasible space, since say this is the point is x1. Now, we will move to x2. This is our next optimal point. Our searching mechanism will be such that x1 will move to x2, then it will move to x3. In the next iteration, it will move to x4. In the third iteration, then it will move to x5. That is the corresponding optimal point, where x5 is the optimal point for the given problem. Okay. This is the searching technique for us. How really we did it? If we just see the whole mechanism here, we can see that, let me write down the whole iterative process within as an algorithm. We start our iteration with an initial point with and initial point x1. Now, x1 can move in any direction here, x1 can move in the right, it can go in the north, it can go in the south in this way. Now, we need to find that direction which gives us the better value for the objective. Not only that, we will be restricted within the feasible space. That is why one of that possibility is x2. If I move from x1 to x2, that means we have decided that I will move through this direction. This is one part, and the second part is that the thing will be such that if I move from x1 to x2, there is a step length. I will jump from here to here. That is why step 2 for this iterative process would be find a suitable direction. Let us consider the first initial point is xi instead of x1, because I will start from 1, 2, 3, 4 like that. I am making the iterative process more general. Find a suitable direction si and appropriate step length lambda I. Once it is being selected, Si and lambda I is being selected, we will move to step 3. How? We will go for the new approximation of the optimal point. That is xi plus 1. I am starting from ith step, I am moving to xi I plus 1. What is the formation of the xi I plus 1? It should be xi plus lambda I and si, where lambda I and si are the, we have chosen the suitable direction and the corresponding step length in the ith step. Once we are reaching to xi I plus 1, our next task would be to find out that whether xi plus 1 is optimal or not. How to check the optimality? There are certain mechanism for different problem. I will discuss further on that. That is why we will check whether xi plus 1 is optimal or not. If optimal, stop the iterative process. That means we will stop our movement. If it is not, then we will repeat from step 2 to 4 again and again, unless otherwise we are reaching to optimal point. Whatever I have written here, the whole algorithm, let me explain with this problem again. I am starting from x1 I is equal to 1 with suitable direction S1 and the appropriate step length lambda 1. I am moving to x2, that means x2 is equal to x1 plus lambda 1 into s1, and we have checked s2 is the optimal, is one of the feasible point, but that is not the optimal, because there is a possibility for further improvement. That is why we are repeating the process. We are moving to step 2 again. We are selecting the S2, the suitable direction, and the appropriate step length lambda 2, and we are getting the next, the point, that is x3 as x2 plus lambda 2 into s2. Again we are moving to x4, then we are moving to x5. x5 is certainly optimal, because if I just proceed further, I will be out of the feasible space. That is the whole searching mechanism is based on this appropriate procedure. Now, there is certain thing to be discussed here. The efficiency of this searching technique is totally dependent on the proper selection for the step length lambda I and the direction si. Otherwise, if the the selection for lambda I and Si is such that it is either it is guiding me to move from the feasible region to out of the feasible region. Otherwise, this could be another thing I can mention here. If the step length is very small, then number of iterations will be more. That is why finding a proper step length will reduce my computational procedure. That is why this could be general iterative process. Now, this is the general thing I am discussing. This is a numerical technique we are now I am discussing for the constraint, and as well as for unconstrained nonlinear programming problem also it is more applicable. Now, let us start our discussion with the single variable unconstrained nonlinear programming problem. That is the most simplest case for this. That is why I am moving to the next part, that is the numerical method for solving unconstrained nonlinear programming, where single decision variable is involved there. That is why I am moving to single variable optimization technique. There is certain procedure for solving a single variable nonlinear programming problem where there is no constraint. That is why we are dealing with single variable optimization NLP, that is a nonlinear programming problem which is unconstrained. There are several techniques for solving it. If I just refer my previous lecture, there are certain analytical procedure that is mostly dependent on the class, that is more specifically that is a classical optimization techniques, and there are certain other methods also, that is the numerical methods which I am discussing today. Now, numerical methods can also be divided into two categories. One category is the region elimination technique, and another category is the interpolation method. I will discuss each and every methods with specific example and corresponding algorithms. Now, region elimination technique, again there are several techniques are available. Most simplest technique is unrestricted search procedure, and another procedure is the exhaustive search. The next one is the dichotomous search. Next is the interval halving technique or bisection. Next is the Fibonacci method. Then is the golden section method. All these methods are these are mainly can be categorized as a region elimination technique. What is the meaning of that? I will tell you later on. Now, coming to the interpolation method, there are two types of interpolation method. One method is dependent on the derivative of the function. That is why we can name it as a derivative based techniques, and the other method which is not dependent on the derivative of the function. Now, in this category non-derivative methods, non-derivative based methods, the one of the most popular method is the quadratic interpolation technique. But for the derivative based techniques, one of that is the cubic interpolation technique, then is the Newton method, then is the quasi-Newton, then is the second method, and we are using these few methods in our numerical numerical techniques also, numerical problems also. Now, these are the methods I will discuss one by one, but if I just move to the region, I will start my lecture with the regional elimination technique. Now, if I just move here, we could see that there are several methods, but all the methods are having its own advantages and disadvantages. Few methods are very easy to compute, computational process is very simple, but we will see that the method is not efficient. That is why whenever we are discussing the searching mechanism, searching technique for getting the optimal solution, one part is very important for us. We need to check the efficiency of the corresponding searching technique. Now, in these methods, dichotomous interval having Fibonacci golden section method, these methods are being one of the, we can categorize as a sequential search procedure, because sequential search procedure, it utilizes the information generated in the previous iteration in placing the subsequent iterations in the iterative process. That is why we are we will discuss the region elimination technique and most specifically the unrestricted search method in the next. Now, region elimination technique is mostly based on one of the most important assumption, that is the function must be unimodal in the specified domain of definition. That is more important for the region elimination technique. That is why let me write down the assumption for this. For the region elimination technique is that the function means the objective function, I mean to say, because there is no constraint for the corresponding optimization problem, and the function is for the function there is a domain of definition, and we are assuming that function is unimodal in the specified domain of definition. What is the definition of the unimodal? That would be our next task to learn. Within the specified domain of definition. Now, whenever the function domain of definition means, that is the domain of the corresponding decision variable, and we are dealing with a single variable. That is why describing the unimodal definition is much easier for us. If the function is multimodal means the function is having several peaks or several valleys, several maximas or minimas within the specified domain, we will just subdivide the parts of the domain in such a way that the function is unimodal in the corresponding in the respective parts, and we will search for the optimal solution within that specific region where the function is unimodal. And unimodality assumption will lead to the conclusion that always we will find out the local optimal in the given range. That is why let us now define the unimodal function. For example, if I just draw the graph, it will be clear to you. For example, this is the domain of definition, it is starting from A, this is our decision variable axis, and this is the corresponding objective function f, and the function is defined from A to B. From the figure it is very clear that function is having only one minimum at this point. That is why we can say the function is unimodal in this range. That is why formally let us introduce the definition of the unimodality. A function f x is said to be unimodal if certainly on the interval a to b, if it is monotonic in either side, monotonically decreasing in the left part and the monotonically increasing in the right part on either side, and x star, that is my x star is the optimal point within the interval if it is satisfying the following conditions. Within the interval and monotonic ideation, extra is the optimal solution, then if fx1 is greater than fx2. What is fx1 and what is fx2? Let us consider this is fx1, this is the corresponding x1 in the decision variable space, and this is the corresponding x2 in the decision variable space, that is the domain of definition. Then we could see fx1 is greater than fx2, then this implies that optimal solution must exist within x1 to b, but optimal solution cannot be within a to x1. All right. And the second condition, if, let me take another case, function is this way, this is the domain of definition from a to b, this is my x1 and this is my x2, certainly the optimal point, this is x star for us. If fx1 is lesser than fx2, this implies that x star must be within a to x2, and the other condition is that the optimal point cannot be within a x1 to b, x2 to b, sorry. This is the condition for the unimodality. That is why, because the function is having only single optimal point in this region and this is monotonic in either side. If I just move from here to here, this is decreasing, this is increasing. If x1 is greater than x2, that we have written that the optimal solution will be in the part from x1 to b, it can't be from a to x1. And if the fx1 in this case is lesser than fx2, then certainly the optimal point will be from a to x2, it can't be from x2 to b, because there is only one minimum point within the definition. Now, there is another definition is that f is strictly unimodal. If the function is unimodal, this is one of the condition, and the second condition is that there does not exist any subinterval within the range a to b where the function is having constant value. Then only we can say the function is strictly unimodal. Now, this is the definition altogether regarding the unimodal function. Now, I am moving to the next. What is the region elimination strategy we are adopting for region elimination technique? That is the part I am discussing now. That is why we will move to the next, that is the region elimination strategy we will adopt in general for any region elimination technique which are being listed in my previous slide. The region elimination strategy is mostly based on the definition, is mostly based on the assumption that the function is unimodal in the given range. Now, let us start our discussion for the minimization problem, and we are assuming that function is unimodal, and not only that, function is having one minimum point within the domain of definition. That is why we are assuming the function f, we need to minimize f of x where x is in between a to b, and we are assuming that function is unimodal. This is the assumption for us. Function is unimodal and x star is the corresponding optimal point, that is the minimum point where x star is in between a to b. As I have discussed about the iterative process, that is why the process is mainly based on the technique is that we will start from a guess point, we will start from an initial point from where we will start our journey, and we will move to the next improved approximation for the corresponding optimal point with some iterative process. And that iterative process is based on this region elimination technique. That is why I am discussing now the thing is that such starting with an initial point, starting with the initial guess point, and we will move to a sequence of improved approximations. So, that let us consider that x1 and x2, there are 2 points within the domain of definition where x1 is lesser than x2. Now, once we are moving to the next optimal, what is the strategy we are following is that if fx1 is greater than fx2, then minimum must lie, that is x star must lie within x1 to b. Just from the definition of the unimodality it comes. That is why in the next iteration we will just restrict ourselves within the region from x1 to b. We will start our process by taking the initial interval, that is called the initial interval of uncertainty from a to b, and we will see if fx1 there are 2 points we will take within the region. If we see fx1 is greater than fx2, then we are sure that the minimum must lie within x1 to b. That is why we will just discard the region, we will discard the interval a to x1 in the next iteration. But if it is the other case, if fx1 is lesser than fx2, then minimum must lie within a to x2. That is why in the next iteration we will just discard the interval x2 to b. We will eliminate the region, and if we see the other case, if fx1 is equal to fx2, then certainly the minimum will lie in between x1 and x2 because the function is unimodal. I can just draw a graph in this case. For example, this is the graph for me, this is x1, this is corresponding x2, and from the figure it is very clear that fx1 is equal to fx2 and minimum is in between this and this. And in this case we will just eliminate in the next iteration, eliminate the intervals certainly from a to x1 and x1 to x2 to b, all right. And we will restrict ourselves within x1 to x2. Again we will take 2 points here, we will just see whether at one point functional value is greater than or less than the other one or not. We will just eliminate the corresponding interval. In that way we will proceed further and further. And the beauty of this region elimination strategy is that in every time we are discarding a part of the interval, so that our searching region will be lesser than the previous iteration. That is the technique for us. Now, let us start our discussion with the unrestricted search technique, that is one of the basic region elimination technique, and we are discussing now unrestricted search. Search mechanism. As you know, for any searching technique, as I have discussed, there are 2 things, one is the direction and another is the step length. And we are discussing the most general unrestricted search technique, more simpler unrestricted search technique with fixed step length. And the direction, certainly since we are considering the single variable optimization, that is why we are restricted to move to in the real line. That is why if I just start from our journey from one of the point in the real line, either I can move to the right or I can move to the left. If I move to the right, then the searching direction would be plus sign, and if I just move to the left, the searching direction will be minus. That is why either I will just jump from one point to the other point with the step size plus lambda, or we will with the step size minus lambda. This part I will discuss now. Let me just write down the corresponding algorithm of the unrestricted search technique. Here also the same thing. I will discuss the whole searching unrestricted search technique and the other things with some example in the next. Search with an initial guess point or the trial point xi. I can start from 1, 2, 3 etc. That is why start with I is equal to 1. Next step, obtain the new approximation. How? With the same technique. That xi plus 1 is equal to xi, let me take it capital X, xi plus lambda I into si. Now, let us note in this case that si is equal to plus 1 or minus 1 and lambda I is equal to lambda for all steps, because we are considering the fixed step size lambda here. Now, we are moving to the next, that is why x1 is going to x2. How? Either it is x1 plus lambda or x1 minus lambda, and we will check the optimality. How to check the optimality? Checking optimality means we will just check whether there is any possibility for the improved objective functional value or not. That means we will just check whether we are getting the better objective functional value within by considering the corresponding domain of definition, that is the corresponding range of the decision variable. Now, if I just move from one initial guess point to the other point, I will just check whether fxi is greater than fxi plus 1 or not. If fxi is greater than fxi plus 1, that means we are getting better functional value. Since we are considering the minimization problem, that is why we will prefer the better minimum, that is the lesser functional value. That is why xi plus 1 is most preferable for me, and we will just move to the next step with si is equal to plus 1. And how? We will repeat. If I just write down the algorithm, I can write it down in this way. Repeat step 2 with si is equal to plus 1 until fxi plus 1 is greater than fxi. That means we are not getting improved approximation in that case. All right. If it is the other case, that is fxi is lesser than fxi plus 1, then we will repeat the process. Repeat step 2 with si is equal to minus 1. How long? The same condition until fxi plus 1 is greater than fxi. That is why in the previous case I can say xi plus 1 is equal to xi plus lambda. In the second case, we will consider xi plus 1 is equal to xi minus lambda. That is the consideration in the next case. That means we are moving to the left, because if I move to the right, we will get the unimproved approximations. All right. And if I just see, we are mostly dependent on the region elimination strategy I have just discussed in the previous case. And one thing I must again mention here, we are considering that function only in the unrestricted search where the function is unimodal in the given domain of definition. If the function is multimodal, in the similar case we will just consider we will subdivide the interval into different parts so that the function is unimodal in the respective parts, and we will proceed in that way. Now, there can be another possibility that fxi is equal to fxi plus 1. That means that function is the third condition for the region elimination strategy, that function is having minimum within xi and xi plus 1. That is why we will start again our procedure from step 2 again. Okay? That means minimum is within x1 xi rather to xi plus 1, and we will start our journey in that way. That means if this is the case, this is my xi, this is my xi plus 1, and I know the minimum is here. That is why we will discard this region and that region. Again we will take a guess point here. We will move either in the right or in the left according to the condition whether we are getting better functional value or not, and with these two conditions separately we will move to the next and we will proceed further. We will repeat the process until and otherwise we are not getting any better functional value. Let me explain this procedure with a simple example in the next. We are considering a simple example here. Consider for problem of minimization again, and we are trying to minimize fx, that is x into x minus 4, that is a nonlinear function of a single variable x, and here it is given that x is in between 0 to 4, that is the domain of definition, and it is also given that the function is unimodal. If I draw the graph, I will see the function is unimodal within the range 0 to 4, otherwise it is given to us, and it is also given that start with the initial guess point or the trial point as 1, start with x1 is equal to 1, and the step size lambda is equal to 0.1, 0.1. All right. If this is the case, we will just do the entire thing. We will start from x1, this is my 0 to 4 and this is my 1. If I start from x1, let us see what is the functional value at 1. The functional value at 1 is certainly minus 3. That is why I know that I have to move, I have to jump to the next point with the step size 0.1, but I do not know in which direction I will move. I can move in the left direction, I can move in the right direction as well. If I move in the right direction, I will see whether we are getting better functional value, or if I move in the left direction, we are getting better functional value. That is why let me take 2 points in either side of 1, that is we are considering 0.9, x equal to 0.9, and we could see that the functional value is coming minus 2.79, and if I just move to 1.1, we could see that we are getting the value. Then what is the conclusion for us? The conclusion is that if I move to the left, then we are getting the functional value which is higher than the functional value at 1. That means, and the function is unimodal. That is why the minimum cannot lie in between 0 to 0.9, I am sure for that. That is why I will move to the right hand side, because in the right hand side we could see that if I just move to a 1.1, the functional value at 1.1 is minus 3.19. That means it is better value than the 1 value. That is why if I move further from 1.1, there is a possibility that we will get the better value for the function fx. Better in the sense that function is minimization, better means we will get the lesser functional value, that is more acceptable in this case. Alright. That is why we can conclude that minimum must lie within 1 to 4. That is the conclusion for us. We are discarding the region, we are eliminating the region from 0 to 1 in the next case, and we are moving to the moving further. That for that thing, the whole information can be tabulated in this way. Just see. The first step, we are considering x1 as 1, x2 as 1.1. This is the corresponding functional value -3 and -3.19. Certainly, fx1 is fx2 is lesser than fx1. That is why the condition fxi is lesser than fxi plus 1, this is not fulfilled, and that is why we have written no. That is why we will move to the next. Where to move? From 1.1 we will move to, with the step size 0.1 we will move to the right, that is 1.2. That is why just see the next. The second step, from 1.1 we are moving to 1.2. For this thing the functional value is changing from -3.19 to -3.36. That means we are getting better functional value. That is why there is a possibility to proceed further. Let us see what is happening in the next. We are again moving from 1.1 to 1.3, and just see we are getting better functional value. That means the lesser functional value in this case. Again there is a possibility to improve further and further. Let us see what is happening. We are moving from 1.3 to 1.4, better functional value. 1.4 to 1.5, again the better functional value. We started our journey from -3, and we see we are getting better and better functional value and reaching to the functional value as -3.84. Again we are moving to the next, from 1.5 to 1.6, better functional value. For the next 1.6 to 1.7, better functional value, 8, better functional value. In this way, if I just move to the point 1.8 to 1.9, we could see the functional value is coming again better, -4.0. But if I just move from 1.9 to 2.0, we see that the functional value is now lesser value, the higher value. That is why we will stop our journey at 1.9, and we will declare that the optimal point, the minimum point must be 1.9, and the corresponding functional value is -4.0. All right. This is the case. Now, we will stop our iterative process. That is why we could say that x star is equal to 1.9 and the corresponding functional value is f x star is equal to -4.0, and this is my conclusion. Whatever logic we have adopted for the minimization problem, if I just consider the maximization problem, we will just adopt the reverse logic. We will conclude that we are getting the better functional value if the functional value is increasing instead of decreasing. Okay, that is the case for us. Coming to the next. We will move to the next, that is the unrestricted search technique with accelerated step size. Now, just look at this table. How many iterations we had to perform? Here we had to perform 10 iterations. Now, that is why one advantage is that this process is easy to implement. We can do it manually, or we can write a simple program to just to get the to implement the iterative process, so that within 10 steps we will reach to the optimal solution. That is why as an advantage of this method I can mention that it is easy to implement. But there is a disadvantage. Disadvantage is that selection of the initial guess point is more important for us. If the initial guess point is given to us, that is fine. If it is not given, if I select randomly within the region 0 to 4, there is a chance that I need to do more number of iterations. That is why selection of initial guess point is much more important thing for us. Not only that, selection of step length, though we are considering the fixed step length, but still if the step length is not proper one, there is a chance that I will be out of the optimal point within fewer steps. Now, that is why it may happen that we will start our journey from the initial guess point and we will just move to with the corresponding step length, but it may happen that we will far from optimal point if the step length is very high. But if the step length is very small, number of iterations will be more. That is why if we have some mechanism so that if I see the functional value is increasing and increasing further and further with the step length 0.1, if there is a mechanism that I will change the step length in between from 0.1 I will move to 0.2, then in that case instead of 1.1 to 1.2 I will just directly move from 1.1 to 1.3, alright. In that case if I see the functional value is again better one, I will just proceed with the same step length or with the accelerated step length, so that the number of iterations we could reduce. Then the searching procedure will be much more efficient. That is why we are having the next stage of searching technique, that is called the unrestricted search with the accelerated step length. What is the thing is that in the process we can increase the step size, it can be doubled, it can be tripled or more, as long as the functional value is improving. That is why let us consider the same example here and let us see whether with the accelerated step size we are getting better optimal or not. And this is a case for this. We are starting with the step length lambda is equal to 0.1. Now, we are moving from 1.1 to 1.1, 1.0 to 1.1. This is my starting point 1, it was given there. Now, functional value is better. That is why there is a chance for improvement. Now, I am increasing the step length, instead of 0.1 I am making it 0.2. Then 1.1 to 1.3 we are getting better functional value. Let me do a try. We are changing the step length again from 0.2 to 0.3. That is why 1.3 will move to 1.6. Again we are getting better functional value. Again we are changing the step length 0.4. We could see that we are getting better functional value. I can move to the next with 0.5 and we could see that from 2.0 it is just jumping to 2.5 and we are getting not better functional value, we are getting the higher value of the objective function. That is why we have to stop here. That is why if I just stop our searching procedure, we will declare in the present situation is that 2.0 is the corresponding 2.0 is the corresponding functional value for it, alright. But one thing it is clear that there could be, we have increased the step length from 0.4 to 0.5, in between the optimal value we are missing. That is why we can revise our procedure in that way that we will reduce the step length. Instead of taking 0.4, we can take it 0.04. In that way, we will move further and further. We can fine tune our optimal solution. In that way, we can develop the unrestricted search technique very nicely. Okay. This is altogether unrestricted search. Now, we are moving to the next, that is a little bit complicated than the unrestricted search technique, that is the exhaustive search technique. The exhaustive search procedure is mainly based on this Assumption again, the function must be unimodal within the domain of definition. This is my functional value, certainly the minimum is lying here. This is the domain of definition A to B, and the process is such that we will just divide the whole interval of uncertainty, initial interval of uncertainty, into n plus 1 equally spaced subintervals. That is why I will go to x1, then x2, then x3. In this way we will go to xn. How many parts are there? 1, 2, 3, 4 up to n plus 1. That is why initial interval of uncertainty is divided into n plus 1 equally spaced subintervals. Then we will see the functional value at each and every point of the given within the given range. If minimum occurs, here is the minimum for us, minimum occurs at xk, then we will say that final interval of uncertainty will be xk minus 1 to xk plus 1. Final interval of uncertainty would be from xk minus 1 to xk plus 1. Then what is the corresponding length for it? Certainly the corresponding length would be 2 into b minus a divided by n plus 1, alright. Otherwise, if I say that L0 is the initial interval of uncertainty, that is from A to B, where the A to B, no, actually this is the length of the initial length. If I consider the length of the initial interval of uncertainty A B as equal to B minus A, then Lk can be written as 2 into L0 divided by n plus 1, alright. Now, our next thing is that we have to find out the functional value at each and every point where the functional value is minimum, we will stop our thing. Now, there are few things to be discussed in this regard, that in the exhaustive search we have seen that we have to subdivide the interval into n plus 1 equally spaced subintervals. That is why our next task is to find n, that is more important. The value of n is totally depends on the fact that what accuracy I want regarding the optimal solution. Shall I allow the 10% error, or shall I allow the 5% error on the initial interval of uncertainty? Depending on that, we will select the corresponding n. That is why there is a measure for any region elimination technique, that is called the efficiency of the searching technique, rather the measure of efficiency. This is also named as the reduction ratio. This is equal to ln by L0. That means after n iterations, what is the interval of uncertainty and what was the previous interval of uncertainty. Depending on that, we will select that is why there is a part I have to discuss further. Though we are discussing several searching procedures, we will discuss in the next that which method is more efficient, and that will totally depend on the reduction ratio value. And here I am just concluding my lecture today. I will start my next lecture with this exhaustive search procedure with some specific example. Thank you.